What if everything you see around you, your home, the sky, even the stars, exists on just one layer of an infinite cosmic stack? Picture our universe not as an isolated bubble floating in nothingness, but as a single sheet in a vast, multidimensional library where countless other realities press against ours like pages in a book. This isn't science fiction, it's the mind-blowing premise of Brane Theory, a frontier idea in physics that could rewrite our understanding of existence itself. Brane Theory proposes that our universe might be a membrane, or brane, floating in a higher dimensional space alongside other branes, each hosting its own version of reality. Think of it like floors in a skyscraper. We live on one level, completely unaware of the worlds above or below us, separated not by distance but by dimensions we can't perceive. These unseen layers could harbor alternate histories, alien laws of physics, or even mirror versions of ourselves. And here's the kicker: under the right conditions, these branes might collide, merge, or ripple, events so colossal they could explain cosmic mysteries like the Big Bang itself. But why should this matter to you? Because if Brane Theory is true, it wouldn't just change textbooks, it would redefine what's possible. Imagine tapping into the energy of parallel universes, communicating across dimensions, or unlocking technologies that seem like magic today. The implications stretch from quantum computing to cosmology, even shaping how we think about consciousness and destiny. This isn't just about distant galaxies or abstract math, it's about the fabric of your reality. So buckle up. Over the next duration of video, we'll unravel how this radical idea emerged, the science behind it, and why it might be the key to humanity's next evolutionary leap. The journey starts now. To grasp the wild idea of Brane Theory, start by thinking of our universe not as a lone island in space, but as a sheet of vast, stretchy membrane floating in something far bigger. These sheets, called branes for short, aren't just hypothetical doodles, they're core to string theory, one of physics' most ambitious attempts to explain everything. Imagine a stack of newspapers. Each page is its own world, filled with stories and rules, completely separate unless something or someone presses them together. Now picture those pages aren't flat, but vibrating, writhing surfaces with extra dimensions we can't see. Our entire cosmos might exist on one of these membranes, drifting through a higher dimensional space scientists call the bulk. To us, the bulk is invisible, like the air to a fish, but just as air allows birds to fly in 3 dimensions while fish swim in 2, the bulk could be the hidden arena where other universes dance right beside ours. This isn't just poetic speculation. Physicists like Randall and Raman Sundrum showed how these branes could warp the fabric of reality itself. Their groundbreaking models suggest that gravity, the force that pins us to Earth, might actually be leaking into our brain from another, explaining why it feels so weak compared to other forces. Think of it like a magnet on a table. The pull you feel is faint because most of its power is seeping through the wood. Here's where it gets even stranger. If another brane floated close to ours, its vibrations might ripple into our universe as cosmic echoes, energy bursts with no clear source, or ghostly particles that appear and vanish. Some scientists even speculate that the Big Bang wasn't a singular explosion, but a collision between branes, a cosmic car crash that birthed time and space as we know it. Visualizing this is tricky, but try an old trick from geometry class. Remember how a circle is just a slice of a sphere. To a 2-dimensional being living on that circle, the sphere would seem impossible, even silly. We're in the same boat, trapped in our 3-dimensional brain, blind to the fuller picture. The math hints at it, the experiments are chasing it, and if we're right, the next breakthrough won't just add a chapter to physics, it'll tear up the whole book. At the heart of Brane Theory lies a radical idea from string theory, the notion that everything in existence, from stars to your morning coffee, might be built from unimaginably tiny vibrating strings. These aren't the strings you'd find on a guitar, but fundamental threads of energy, each dancing to its own rhythm in the quantum symphony of reality. String theory demands these vibrations happen not in the familiar 3 dimensions we experience, but in 10 or even 11, a cosmic landscape where extra dimensions are curled up so tightly they're invisible to us, like the grooves on a vinyl record too fine for the naked eye to see. Now here's where it gets wild. Our entire universe could be one of many membranes, a 3-dimensional brane floating in this higher dimensional space. Picture a soap bubble drifting in a room full of other bubbles, each its own self-contained world. The way these strings vibrate on our brain determines the laws of physics we experience, the speed of light, the strength of gravity, even the existence of atoms. But on another brane, strings might hum a different tune, creating alien physics where black holes are commonplace or time flows backward. This isn't just abstract noodling. The math suggests these extra dimensions could explain why gravity is so weak compared to other forces. Most of its influence might be bleeding into neighboring branes. Imagine shouting into a pillow. Your voice is muffled because the sound escapes into the fabric. Similarly, gravity's faintness in our universe could be a clue that it's not confined to our brain at all. Yet string theory remains controversial. After decades of research, there's still no direct experimental proof these tiny strings or hidden dimensions exist. Critics argue it's more philosophy than physics, a beautiful idea that's yet to make testable predictions. But supporters counter that the math is too elegant to ignore, and that future breakthroughs like detecting gravitational waves from brane collisions could change everything. The stakes couldn't be higher. If string theory and brane theory are correct, we're not just reimagining particles or forces, we're rewriting the very definition of reality. Every law we take for granted, from quantum mechanics to relativity, might just be local bylaws on our tiny slice of the cosmic stack. And somewhere out there in the bulk, another brane's strings could be vibrating an entirely different universe into existence. The Ekpyrotic Universe model takes brane theory to its most dramatic extreme, suggesting our entire cosmos might be the aftermath of a cataclysmic collision between 2 higher dimensional worlds. Imagine 2 enormous sheets of reality drifting through the bulk, drawn together by forces we can't yet measure, until bang, they slam into one another with unimaginable force. This isn't just a cool visual, it's a serious alternative to the Big Bang, one that could solve mysteries that have puzzled cosmologists for decades. In this model, the violent energy of that brane collision didn't just create matter, it became matter, flooding our newborn universe with the raw ingredients for everything we see today. Think of it like clapping your hands underwater. The shock waves ripple outward, forming temporary structures before fading away. Only here, those ripples froze into galaxies, stars, and planets as our brane rebounded from the impact. And because the collision happened across the entire membrane at once, it explains why the universe looks so uniform in every direction. No need for the inflation patch that standard cosmology relies on. What makes this idea so compelling isn't just its audacity, but its problem-solving power. The classic Big Bang theory struggles to explain why the cosmos appears so finely tuned, why distant regions have nearly identical temperatures when they've never had time to interact. Inflation tries to fix this by proposing a brief period of hyper-expansion, but it's still theoretical. The Ekpyrotic model sidesteps the issue entirely. If our universe began as a single, synchronized collision, uniformity was baked in from the start. But the implications go deeper. If branes can collide once, they might do it again, cyclically. Some versions of the theory suggest these crashes could happen every trillion years, breathing new universes into existence over and over. It's a cosmic reset button where each collision wipes the slate clean while preserving certain quantum traces from the last cycle. That could mean our universe isn't the first, and it won't be the last, just one page in an infinite cosmic flipbook. Of course, there are hurdles. Detecting evidence of a pre-Big Bang brain collision isn't easy, though some physicists hunt for faint imprints in the cosmic microwave background, like finding fingerprints on a window after the storm has passed. Others theorize that gravitational waves from the event might still echo through the bulk, waiting for the right technology to catch them. What's clear is this: if the Ekpyrotic model holds up, we're not just rewriting the story of our universe's birth, we're uncovering a whole new genre of cosmic history. One of the most tantalizing clues that our universe might be stuck to a brane comes from an everyday observation. Gravity feels oddly weak. Think about it. A tiny fridge magnet can defy Earth's entire gravitational pull, lifting a paperclip with ease. Compared to electromagnetism or the nuclear forces, gravity is a featherweight in the cosmic ring. But why? Brane theory offers a striking answer. Gravity isn't weak, it's just diluted, seeping into dimensions we can't see. Here's how it could work. Imagine our universe as a watercolor painting on a sheet of paper. The paint stays mostly on the surface, but some bleeds through to the layers beneath. In the same way, gravity's influence might not be confined to our brain. It could be leaking into the higher dimensional bulk, spreading its influence where we can't detect it. This would explain why gravity's grip feels so faint compared to forces like electromagnetism, which are trapped entirely on our brain like ink on a plastic sheet. But there's a twist. String theory originally proposed extra dimensions were microscopic, curled up tighter than a coiled spring. Brane theory flips this on its head, suggesting some hidden dimensions could be vast, stretching across cosmic distances without us noticing. How? Because everything except gravity is glued to our brain, like actors trapped on a stage, oblivious to the theater's hidden balconies. Only gravity, with its ability to wander off the brain, would hint at the unseen architecture around us. Scientists aren't just theorizing, they're hunting for proof. The Large Hadron Collider, the world's most powerful particle smasher, could unveil these hidden dimensions by spotting missing energy in collisions. If particles suddenly vanish, their energy might have tunneled into an extra dimension, like a marble rolling off a table's edge into unseen space. Even wilder, the LHC might create microscopic black holes, their fleeting existence betraying gravity's extra-dimensional strength. These experiments walk a razor's edge between groundbreaking discovery and dead ends. But that's the thrill of Brane theory. It turns the weakness of gravity from a puzzle into a portal, pointing toward realities stacked just beyond our reach. And if we're right, the day we detect even a whisper from the bulk won't just solve a physics problem, it'll crack open a door to the multiverse. Quantum mechanics doesn't just govern particles in our universe, it might also hold the key to secret tunnels between branes. Picture the fabric of reality not as a rigid sheet, but as a frothing ocean where tiny bubbles of energy constantly pop in and out of existence. These quantum fluctuations, normally too fleeting to notice, could, under the right conditions, punch microscopic holes in our brain, allowing particles or even information to slip into neighboring realities. It's like two soap films momentarily merging when a breeze pushes them together, exchanging droplets before snapping apart again. Some theories suggest these quantum bridges could create brain bubbles, pockets where a new universe pinches off from an existing one, like a blister forming on hot plastic. These budding baby universes would inherit their parent brain's laws of physics, but might evolve in wildly different ways, birthing cosmic cousins with alien constants or extra dimensions. The math even hints that such events could leave scars, subtle wrinkles in the cosmic microwave background, the afterglow of the Big Bang. Astronomers are already sifting through this ancient light for anomalies, unexplained cold spots, strange swirls, or patterns that seem too precise to be random. A telltale signature of a brain collision might look like a bruise on the sky, a circular imprint where another universe once brushed against ours. For observers inside a colliding brain, the experience would be beyond surreal. One moment, the night sky might shimmer with impossible colors as foreign physics bleeds into ours. the next gravitational waves could rip through planets like a shockwave in slow motion. Time itself might stutter, with clocks running backward in patches or particles aging decades in seconds. And if information did cross between branes, we could receive cosmic Morse code signals encoded in particle decays or sudden bursts of dark energy with no local source. Of course, this is all speculative for now, but the audacious beauty of these ideas lies in their testability. Future telescopes tuned to ultra-precise frequencies might catch echoes of brain interactions in the cosmic background, while quantum experiments could search for particles that wink out of existence only to reappear with strange properties. If proven, these phenomena wouldn't just confirm Brane theory, they'd reveal our universe as a single thread in a tapestry of realities, each brushing against the others in a quantum dance we're only beginning to imagine. Parallel universes aren't all created equal. The idea of multiple realities splits into two wildly different flavors: quantum, many worlds, and brain-based multiverses, each painting a distinct picture of how alternate versions of you might exist. The many worlds interpretation, rooted in quantum mechanics, suggests every decision spawns a new timeline, branching infinitely like a fractal tree. Missed a bus this morning, somewhere, a version of you caught it and is living out the consequences. But Brane Theory's multiverse isn't about choices splitting reality. It's about entire cosmic neighborhoods stacked like apartment floors, separated by dimensions we can't cross. Here's the mind bender: those alternate branes could be physically close, just millimeters away in a hidden fourth spatial dimension, yet utterly unreachable. Imagine two people trapped on opposite sides of a pane of glass. They're inches apart, but without a way to move through the glass, they'll never meet. That's the Brane multiverse, parallel realities pressed together like pages in a book, each with its own unique physics, history, and maybe even life. While many worlds clones you endlessly across timelines, Brane Theory might host a you built from entirely different particles. Or no you at all. The philosophical whiplash is real. Many worlds offers a comforting democracy of possibilities. Every version of you is equally real, just on different branches, but branes, they're more like distant cousins than twins. A neighboring brane could have no stars, no atoms, or laws where time runs backward. Other yous might not exist there unless the conditions for life repeat by cosmic coincidence. This isn't just theoretical sparring, it reshapes how we search for proof. Many worlds leaves traces in quantum experiments, like particles seemingly remembering alternate paths. Brane Theory's evidence might lurk in gravity's quirks or sudden bursts of energy from colliding membranes. One multiverse feels intimate, a hall of mirrors reflecting endless versions of now. The other is vast and alien, a library where every book obeys different rules. The question isn't just are we alone, it's which multiverse are we even in? Dark matter has long been the cosmic ghost story of modern physics, an invisible something that outweighs visible stars and galaxies 5-1, yet refuses to show itself. But what if the answer isn't hidden in our universe at all? Brane Theory offers a spine-tingling alternative. Those mysterious gravitational tugs we blame on dark matter might actually be the fingerprints of parallel universes brushing against ours through hidden dimensions. Picture a galaxy spinning like a carousel. According to Newton's laws, stars on the outer edges should move slower than those near the center, but observations show they whip around at nearly the same speed, as if tethered by invisible ropes. Astronomers proposed dark matter as the unseen anchor, but after decades of searching, its particles remain elusive. Now imagine those missing ropes aren't in our universe at all. They're strands of ordinary matter from a neighboring brane, its gravity leaking into ours through the higher dimensional bulk. Like feeling the warmth of a fire through a wall, we detect the pull without seeing the source. This isn't just a clever workaround, it's a testable hypothesis. If dark matter's effects come from another brane, its distribution should carry subtle clues. Unlike traditional dark matter models where particles clump predictably around galaxies, brane-based gravity might leave shadow patterns, unexplained gravitational gradients that align in ways ordinary physics can't explain. Some astrophysicists are already mapping anomalies in galaxy clusters, hunting for distortions that resemble the gravitational wake of a nearby membrane. The implications are staggering. If correct, we wouldn't just solve the dark matter puzzle, we'd prove our universe shares hidden space with others. The extra gravity we've been chasing might belong to stars, planets, or even civilizations in a parallel brane, forever out of reach yet invisibly shaping our cosmos. Future telescopes like the Vera Rubin Observatory could spot these signatures by tracking how dark matter's grip varies across space, searching not for a particle, but for the cosmic breadcrumbs of a collision we can't yet see. Critics argue this swaps one mystery for another, but that's the point. Science thrives when bold ideas push us to ask better questions. Whether dark matter is unseen particles or distant branes, the truth promises to rewrite our place in the multiverse. And if we're lucky, the next gravitational anomaly we detect won't just be data, it'll be a handshake from a universe next door. Time doesn't march to the same beat everywhere, not if Brane theory holds true. On another membrane floating just beyond our perception, clocks might tick slower, faster, or even in unpredictable bursts, warped by gravitational forces or the brane's own motion through the higher dimensional bulk. Picture two ships sailing side by side on a turbulent ocean. One rides the waves smoothly while the other is tossed by unseen currents. For passengers aboard each ship, time would feel normal, but if they could compare watches, the difference would be staggering. Now replace those ships with branes, and you've got a cosmos where time itself is fluid, a patchwork of realities slipping in and out of sync. This isn't just a thought experiment. Einstein taught us that gravity bends time clocks tick slower near a black hole than on Earth. Brane theory takes this further, suggesting that a neighboring membrane with stronger gravity or higher energy could drag time to a crawl relative to ours. Imagine living on a brane where a single hour stretches into a century next door. The implications are dizzying. Civilizations might rise and fall in parallel universes while we sip our morning coffee, blissfully unaware. Could this loophole enable time travel? In theory, yes, if you could hop between branes. A traveler moving to a slower time brane and returning might find their original world aged decades in their absence, like a cosmic version of the twin paradox. But here's the catch: without a way to traverse the bulk, it's a one-way ticket. Even if you could cross, the energy required might rip you apart or strand you in a reality where the very atoms of your body obey unfamiliar rules. The wildest twist, some models suggest the Big Bang itself was a time anomaly. If a high-energy brane collided with ours, its version of time, stretched or compressed, could have unleashed the explosive energy that birthed our universe. Think of it like a dam breaking between two reservoirs at different heights. The sudden rush of time's pressure between branes might have ignited creation. While we can't yet test these ideas directly, subtle hints might lurk in the cosmos. Ultra-precise atomic clocks aboard satellites already detect tiny time shifts caused by Earth's gravity. Future experiments could hunt for larger discrepancies, places where time stutters or speeds up without local cause, hinting at a nearby brane's influence. For now, it's a tantalizing maybe, a reminder that time, like space, might be far stranger than we ever imagined. What if the Big Bang wasn't the beginning, just the latest page in an infinite cosmic story? Brane cosmology flips the script on creation, suggesting our universe didn't emerge from a mysterious singularity, but from a spectacular collision between two higher dimensional worlds. Picture two enormous sheets of reality drifting through the bulk, drawn together by gravity or some deeper force until bang, they slam together like cymbals, unleashing enough energy to birth galaxies, stars, and everything we know. This isn't a one-time event. According to the cyclic model, these collisions happen over and over in an endless loop where universes are born, expand, cool, and then collide again, resetting the cosmic clock. The beauty of this idea, it banishes the need for a singularity, that infinitely dense physics breaking point where classical theories collapse. Instead of a baffling start, the Big Bang becomes a phase transition, like water freezing into ice or steam condensing on a window. Energy from the Brane collision floods into our newborn universe, stretching space-time and seeding matter, all without punching a hole in the laws of physics. It's a cosmic reboot where each cycle inherits traces of the last, like echoes of a song played on repeat. Strikingly, this mirrors ancient Hindu cosmology's concept of kalpas, vast cycles where universes are created and destroyed by the breath of the god Brahma. Each kalpa lasts over 4 billion years, ending in a fiery dissolution before renewal. The parallels are uncanny. Both visions reject a linear timeline for a rhythmic, eternal dance of destruction and rebirth. Even the Sanskrit term pralaya, the dissolution phase, could describe the moment when branes drift apart after collision, their energy spent, waiting for gravity to pull them back together. Visualizing this is a challenge, but imagine two taut bedsheets floating in a breeze, rippling as they inch closer. Just before contact, energy builds in the space between them, warping the fabric until, snap, the sheets collide, sending shockwaves racing outward. Those ripples become galaxies, the heat becomes stars, and the rebound, that's the expansion we call the Big Bang. What's revolutionary here isn't just the mechanism, it's the testable predictions. In the classic Big Bang model, the universe's uniformity requires an ad hoc fix called inflation, a hyper-fast expansion in the first fraction of a second. The cyclic model sidesteps this neatly. If branes collide in perfect sync across their entire surface, the resulting universe starts uniform by design. No inflation needed. Even the cosmic microwave background, the afterglow of the Big Bang, might hide clues. Some theorists hunt for faint spiral patterns in this ancient light, potential scars from a pre-collision brane's rotation. Of course, skeptics ask, if this is true, where's the evidence? Future gravitational wave detectors could be key. If a brane collision sent shockwaves through the bulk, their remnants might linger as low-frequency ripples in spacetime, waiting for observatories like LISA to catch them. Others suggest dark energy, the mysterious force accelerating our universe's expansion, might actually be the slow pull of another brane drawing near for the next collision. The takeaway: if the cyclic model holds, the Big Bang wasn't a beginning, it was a turning point, a moment in an endless rhythm where universes rise, fall, and rise again, each collision writing a new chapter in a story without start or end. And somewhere out there in the bulk, another brane might already be drifting toward us, carrying the energy of the next cosmic dawn. The hunt for proof of Brane theory isn't confined to chalkboards and equations. It's playing out in labs and observatories worldwide, where scientists are chasing ghosts of higher dimensions. One of the most promising tools, gravitational wave detectors like LIGO and its upcoming successor, LISA. These ultra-sensitive instruments don't just listen for black hole collisions, they could catch whispers of extra dimensions rippling through spacetime. Here's how: if our universe is a brane floating in the bulk, gravitational waves from cosmic crashes might leak into higher dimensions, leaving telltale gaps in their signals. Imagine clapping your hands in a cathedral. The echoes carry hints about the unseen architecture around you. Similarly, distortions in gravitational wave patterns could reveal the hidden shape of the bulk itself. Meanwhile, particle colliders are probing the opposite end of the scale. The Large Hadron Collider smashes protons together at nearly light speed, recreating conditions fractions of a second after the Big Bang. If extra dimensions exist, these collisions might briefly punch microscopic black holes into existence, fleeting portals where gravity's hidden strength surges. These wouldn't be planet-swallowing monsters, but vanishingly small pinpricks that evaporate instantly via Hawking radiation, leaving behind a spray of particles with missing energy. Spotting this energy deficit would be like finding footprints in snow, evidence of something passing through dimensions we can't see, but the search doesn't stop there. Some theories predict hidden sector particles shy, exotic bits of matter that barely interact with our brain except through gravity. Experiments like ADMX and CAP are tuning into cosmic frequencies, hoping to catch these phantoms converting into photons in strong magnetic fields. It's akin to listening for static on a radio dial where an unexplained crackle might signal contact with a parallel reality. The challenges are immense. Testing a theory about dimensions we can't access is like diagnosing a patient through a brick wall. You're forced to rely on indirect symptoms. Critics argue that without direct observation, Brane theory risks becoming untestable speculation. Yet proponents counter that every major breakthrough once seemed impossible, from black holes to the Higgs boson, until technology caught up to theory. What makes this pursuit electrifying isn't just the potential discoveries, but the sheer creativity of the experiments. From repurposing ancient minds as dark matter detectors to launching atomic clocks into deep space, scientists are turning the cosmos into a laboratory. And if just one of these efforts pays off, the walls of our cosmic room might finally reveal the unseen doors around us. Could consciousness be the one phenomenon in our universe capable of reaching beyond our brain? It's a question that straddles the line between theoretical physics and philosophy, pushing the boundaries of what we consider real. Some researchers speculate that the very nature of human awareness, its eerie, non-local qualities, might hint at connections to higher dimensions. Think of your brain not just as a 3-pound lump of neurons, but as a quantum antenna tuned to frequencies beyond our membrane. When you dream, déjà vu strikes or thoughts seem to arrive from nowhere. Could you be brushing against echoes of another brain's reality? The idea isn't entirely baseless. Quantum mechanics already shows particles behaving in ways that defy classical physics: electrons teleporting through barriers, particles entangled across vast distances. If consciousness arises from quantum processes in microtubules within brain cells, as some theories suggest, it might share this knack for slipping past ordinary limits. Picture a radio picking up faint signals from a distant station. Your mind could be doing the same, intercepting whispers of other brains through quantum static we don't yet understand. Sci-fi loves this trope: characters glimpsing alternate lives in dreams or sensing danger through phantom memories. But strip away the Hollywood gloss and there's a provocative kernel. If brains vibrate in the bulk, their interactions might leave subtle imprints on our minds. Ancient cultures spoke of visions where time folded or realities overlapped. Even modern neurochemistry shows that certain altered states, like lucid dreaming or meditation, can make the brain's filtering mechanisms less rigid, as if tuning out the noise of our brain briefly. Of course, this veers close to pseudoscience if we're not careful. There's zero evidence that consciousness can exit the skull, let alone the universe. Skeptics rightly point out that brains are messy, classical systems, hardly the precision instruments needed to navigate higher dimensions. But dismissing the question outright misses the deeper point. Brane theory forces us to ask where the boundaries of perception truly lie. If our entire universe is just a slice of something vastly larger, why assume consciousness is confined to it? The philosophical stakes are dizzying. If a version of you exists on another brain, does that make your thoughts less singular? Could creativity or intuition be a kind of cosmic interference? Ideas leaking between brains like crosstalk on a phone line. Even if these speculations never yield lab-proof answers, they reframe age-old mysteries about the mind's reach. For now, it's a frontier where physics and metaphysics collide, leaving us with more questions than solutions, but sometimes the right question cracks reality wider than any answer. If Brane theory proves correct, the technological revolution it could unleash would make today's science fiction look like cave paintings. Imagine tapping into the energy of colliding universes, not with solar panels or nuclear reactors, but by harvesting the cosmic shockwaves of branes slamming together in higher dimensions. The energy output would dwarf anything we've ever seen. A single brane collision might release enough power to fuel civilizations for millennia, like striking a match next to a supernova. The trick: building receivers sensitive enough to detect these events and converters capable of handling energies that warp space-time itself. Some theorists propose vast, superconducting nets tuned to gravitational wave frequencies, suspended in space to catch these ripples like a spiderweb snagging dew. Then there's propulsion. A brane drive wouldn't push against the fabric of our universe. It would bypass it entirely, manipulating hidden dimensions to create shortcuts through the bulk. Picture a ship that doesn't move left or right, but sideways into a higher dimension, reappearing light years away without breaking the speed of light. The math hints at possibilities. String theories, wormholes, could be bridges between branes, stabilized by exotic matter with negative energy. NASA Eagleworks lab has already toyed with M-drive prototypes, but a true brane drive would leapfrog such concepts into realms where Alcubierre warp bubbles seem quaint. Materials science would transform overnight. If we could engineer structures that extend into extra dimensions even fractionally, we might create alloys with impossible properties, metals that self-heal by borrowing mass from adjacent branes, or crystals that change their atomic layout in higher dimensions, appearing indestructible in ours. Graphene's strength comes from its two-dimensional structure. Imagine what a four-dimensional lattice could do. Laboratories might one day grow materials in bulk space, harvesting atoms that behave differently outside our brain's constraints. Communication across realities is the wildest frontier. Quantum entanglement already spooks physicists with its instantaneous links. Could entangled particles straddle branes, acting as Morse code taps between universes? Experiments with brane telephones might use neutrinos or dark photons as carriers, particles slippery enough to slip through dimensional barriers. The first message from another brane wouldn't be a radio signal. It could be a sudden, synchronized fluctuation in particle accelerators worldwide, like a knock on reality's door. Of course, these ideas lie at the edge of plausibility today. But recall how Maxwell's equations hinted at radio waves decades before Marconi sent his first signal, or how Einstein's relativity paved the way for GPS. The gap between theory and technology isn't a wall, it's a bridge we build one equation at a time. Brain-driven tech may require energies we can't harness yet or materials that don't exist. But if history teaches anything, it's that the universe keeps its wildest gifts just beyond the edge of impossibility, waiting for us to reach a little further. Hollywood has a knack for taking mind-bending scientific concepts and spinning them into cinematic gold, and Brane theory is no exception. Take Interstellar, where the protagonist navigates a fifth-dimensional tesseract to communicate across time. The film's depiction of higher dimensions as a folded, recursive space isn't just visual poetry, it's a nod to the idea that our universe might be a membrane floating in a larger bulk. When Cooper peers into his daughter's bedroom from beyond the confines of 3 dimensions, it's a dramatic riff on how branes could theoretically allow information to traverse hidden layers of reality. The physics isn't perfect. Of course, real brane collisions wouldn't conjure bookshelf labyrinths, but the metaphor captures the eerie intimacy of a multiverse where every moment touches every other. Then there's Doctor Strange, where the sorcerer's mirror dimension bends and warps like a living origami. The kaleidoscopic cityscapes mirror how higher dimensional space might appear if we could perceive it, walls folding into ceilings, staircases looping into paradoxes. The film's magic, just advanced physics in disguise. When characters sling portals or step through dimensions, they're essentially hopping between branes, leveraging hidden geometries the way string theorists crunch equations. The directors even consulted physicists to ground the visuals in real science, blending artistic license with whispers of actual theory. The one takes a darker turn, exploring a brain-inspired multiverse where versions of the same person exist across realities connected by quantum threads. The premise leans hard into the many worlds trope, but the underlying question is pure brain theory. What if alternate versions of you aren't just hypothetical branches, but neighbors separated by a dimension's thickness? The film's villain, a rogue variant hunting his counterparts, taps into primal fears about identity in a cosmos where duplication isn't just possible but inevitable. Why do these stories resonate? Because they make the unfathomable feel personal. The multiverse isn't just a sci-fi playground. It's a narrative cheat code for exploring fate, choice, and the fragility of existence. When heroes grapple with infinite versions of themselves or villains exploit dimensional rifts, they're acting out humanity's oldest drama, the search for meaning in a universe that might be one of countless copies. Filmmakers also cheat creatively when visualizing higher dimensions. Interstellar uses gravity as a plot device, Doctor Strange trades in fractal psychedelia, and The Matrix, though not strictly about brains, reduces reality to a coded projection, echoing how our universe might be a shadow of higher dimensional processes. These metaphors sacrifice accuracy for emotional punch, but they're closer to truth than we might think. Physicists admit that describing the bulk or brain collisions without analogies is like explaining color to the blind. The trend isn't slowing down. From Everything Everywhere All at Once's chaotic verse-jumping to Loki's time-branching bureaucracy, pop culture is obsessed with the multiverse because it mirrors our fractured, hyper-connected world. Every decision feels amplified when there might be universes where you made the opposite choice. Every relationship carries the ghost of alternate timelines. It's existential FOMO dressed up as science fiction, and Brane Theory, with its stacked realities and hidden dimensions, offers the most tantalizing framework yet for these stories. So the next time you watch a character step through a portal or wrestle with their alternate self, remember, the science behind it might be stranger than fiction. Hollywood's versions are simplified, sure, but they're also a backdoor into concepts that could redefine reality itself. And if one day we prove brains exist, these films might look less like fantasy and more like prophecy. If every decision spawns not just consequences but entire universes, what happens to our sense of purpose? Living in a brain-stacked cosmos forces us to confront the unsettling idea that every version of you that could exist does exist somewhere in the higher dimensional library of realities. A version of you reading this sentence chose vanilla ice cream yesterday instead of chocolate, while another dropped everything to become a sculptor in Paris. The existential weight of this is staggering. Are our choices profound or meaningless when every path is taken by some alternate self? Philosopher Nick Bostrom argues this could be strangely liberating. If all possibilities unfold across the multiverse, regret loses its teeth. Why agonize over the road not taken when some version of you is already cruising down it? Yet other thinkers counter that individuality becomes sacred in a multiverse. David Deutsch, a pioneer in quantum computing, suggests that conscious beings are the universe's way of making meaningful decisions, that even in an infinite stack of realities, your specific choices matter because they define this branch of existence. It's like entering a hall of mirrors. While countless reflections mimic your movements, the original you making choices here and now retains a unique gravity. The ethical ripple is profound. If a near-identical version of you suffers on a neighboring brain, does that dilute your responsibility to ease suffering in this one? Or does it multiply it, knowing pain echoes across realities? The moral math gets dizzying. Utilitarianism, the philosophy of maximizing happiness, might demand we consider all possible versions of beings across all brains, not just our local cluster. But physicist Max Tegmark warns that such thinking could paralyze us. If you spend your life agonizing over every quantum possibility, he quips, you'll miss the bus in this universe. There's a pragmatic case for focusing on the reality we can measure and influence, even if others hum in the background. Then there's the question of identity itself. Buddhism has long taught that the self is an illusion, a temporary assemblage of ever-changing parts. Brane theory gives this ancient idea a sci-fi twist. If you are a pattern of information, why couldn't that pattern repeat on another membrane? Some interpretations of quantum mechanics even suggest consciousness might be a phenomenon that bridges brains, like a radio tune between stations. Theologians wrestle with the implications. Does the soul have a higher dimensional address, or is it bound to a single brain? Perhaps the most radical perspective comes from physicist Andre Lind, who proposed that in an infinite multiverse, every conceivable civilization will eventually develop technology to simulate universes, meaning we might already be someone else's simulation on a higher brain. It's a cosmic Russian doll scenario that makes meaning infinitely recursive, but here's the twist: even if we're shadows on a wall, the light casting us is real. The emotions we feel, the bonds we forge, they're no less vivid because they might flicker across multiple screens. The takeaway isn't answers, it's better questions. Brane theory doesn't erase human significance, it reframes it. We're not smaller in a multiverse. We're part of something vast and interconnected, where every choice spins new threads in a tapestry we'll never see the full shape of. That's not nihilism, it's humility with a side of wonder. After all, if there are infinite versions of you out there, the one reading this right now is the only one asking these exact questions. And that's extraordinary. Across cultures and centuries, humanity's spiritual traditions have painted the cosmos as far richer than the physical eye can see, realms upon realms stacked like layers of an onion. Brane theory's vision of nested universes eerily echoes these ancient intuitions. Take Tibetan Buddhism's Trikaya, which describes reality as threefold: the earthly realm we perceive, a subtle dimension of energy and deities, and an ultimate expanse beyond form. These aren't metaphors but lived truths for practitioners, parallel planes accessible through meditation, much like brains might be reachable via higher dimensional physics. The Dalai Lama himself has remarked that if science one day proved multiple universes, Buddhism would nod in recognition. After all, its scriptures describe Loka's countless world systems where karma unfolds in unique ways, each a self-contained bubble of cause and effect. Sound familiar? Kabbalah's Sephirot offers another striking parallel. This mystical framework maps creation as 10 emanations, vibrational layers through which divine energy cascades into our material world. The Ein Sof, the infinite source beyond the Sephirot, mirrors the bulk of Brane theory, an unfathomable space hosting all possible realities. Jewish mystics even speak of Shevrat HaKelim, the shattering of vessels, where higher worlds fractured during creation, scattering divine sparks into lower realms. It's a cosmic accident hauntingly reminiscent of brain collisions, energy from a higher dimension rupturing into ours, seeding the conditions for life. But does this scientific multiverse erase the need for a creator? Not necessarily. Some theologians argue it expands divine artistry. Jesuit physicist Fr. Robert Spitzer suggests that a God capable of crafting a single universe would hardly be intimidated by a multiverse. It's just a grander studio for creation. Hindu cosmology takes this further, with Brahma endlessly exhaling universes like bubbles from a pipe, each with its own rules and lifetimes. Here, science and spirituality don't compete, they harmonize in scale. Yet tensions exist. Evangelical physicist Don Page counters that fine-tuning. The eerie precision of constants allowing life feels less miraculous if infinite universes exist where anything can happen by chance. But Sufi scholar Nakela flips the script. Perhaps the multiverse is the fine-tuning, with every possible configuration of existence held in perfect balance by a single sustaining will. The most profound dialogues happen where lab coats meet vestments. At Oxford's Ian Ramsay Centre, theologians and physicists trade notes on how brain collisions might align with Christian eschatology. Could the apocalypse, literally unveiling, involve a higher dimensional revelation? Meanwhile, Hindu scientists like Varadaraja Raman see the cyclic brain model as a scientific yuga, echoing the eternal rhythms of creation and dissolution in the Puranas. What emerges isn't a clash but a chorus. Whether through prayer or particle accelerators, we're all reaching for the same truth, that reality in all its layers is deeper than we dreamed. The mystics were right, just not in the way they expected. And if brains hold the key, perhaps the ultimate sacred text isn't written in words or equations, but woven into the fabric of dimensions we're only beginning to sense. The multiverse isn't a single idea, it's a buffet of possibilities, each with its own flavor of reality. Brane Theory's stacked membranes are just one dish on the menu, sitting alongside three other heavyweight contenders: the inflationary multiverse, quantum many worlds, and simulated reality hypotheses. To understand why some physicists bet on brains, let's plate them up side by side. First up, the inflationary multiverse, brainchild of cosmic inflation theory. Picture our universe as one bubble in a frothing cosmic beer, endlessly spawning new bubbles where inflation never stops. Each bubble universe cools into its own laws of physics, forever out of reach. Unlike Brane Theory's membranes drifting in higher dimensions, these bubbles are disconnected, born from quantum fluctuations in an inflating energy field. The kicker: while branes might collide or ripple against each other, inflationary bubbles rarely meet. They're loners in an ever-expanding foam. Then there's the quantum multiverse, where every choice splinters reality into parallel timelines. Miss the bus, one universe branches where you caught it. This isn't about extra dimensions but probability playing out in infinite combinations. The math is elegant, but it lacks Brane Theory's geometric punch. No hidden membranes, just an ever-forking road of possibilities. Yet here's the twist: quantum multiverses could live on branes. Imagine each brane hosting its own set of branching timelines, like a skyscraper where every floor is a hall of mirrors. Now, simulated reality takes a hard left. What if our universe is someone else's computer simulation? No extra dimensions needed, just advanced beings running ancestor simulations like cosmic video games. It's a favorite of tech moguls, but physicists grumble at its untestable core. Brane Theory, by contrast, offers tangible predictions: gravity leaking between dimensions, cosmic bruises from collisions. Simulated realities might explain why math governs nature, but branes explain how. So why do some physicists lean toward brane cosmology? It's the math. String theory's equations naturally give rise to branes, like discovering your recipe bakes cakes you never knew were possible. Inflation requires ad hoc fields. Simulation theory leans on speculation. But branes, they emerge from the numbers tying gravity, quantum mechanics, and higher dimensions into a single package. Even skeptics admit it's a compelling framework, one where the universe's quirks aren't bugs but features. Could these models merge? Absolutely. Imagine inflationary bubbles on branes, each bubble a pocket universe riding its membrane like dew on a leaf. Or simulated realities running within brane-based universes, nested like code in a cosmic server. The lines blur fast. Some theories even suggest quantum branching happens when branes vibrate, with each frequency tuning a new timeline into existence. The Venn diagram of multiverses overlaps in wild ways. Inflation gives us isolation, branes offer connection. Many worlds deal in choices, simulations in code. But together they sketch a cosmos far stranger and richer than any one model alone. Whether any of them are true isn't just physics, it's a referendum on how weird reality dares to be. The holographic principle flips everything we think we know about dimensions upside down, suggesting our three-dimensional universe might just be a shadow cast by a two-dimensional surface, like a movie projected from a flat screen. String theorists like Juan Maldacena have shown mathematically that a higher dimensional space can encode all the information of a lower dimensional one, making our bustling 3D cosmos potentially nothing more than an elaborate hologram painted on some distant cosmic wall. Now fold this idea into brane theory and things get even wilder. If our universe is a brane floating in higher dimensional space, could it also be a holographic projection of another brane, like two sides of the same coin, separated by dimensions we can't perceive? Maldacena's groundbreaking work on the AD/CFT correspondence proved this isn't just metaphor. He discovered that a theoretical 5-dimensional universe, packed with gravity and warped spacetime, could be perfectly described by a 4-dimensional quantum field theory living on its boundary. It's like having a VR headset that simulates an entire world, but the code running it fits on a flat chip. Apply this to branes, and suddenly, the membrane hosting our universe might not be the real thing, just one slice of a deeper hologram. To visualize this, think of an optical illusion where a 3D object seems to pop out from a flat pattern, like those Magic Eye posters from the 90s. Your brain constructs depth where none exists. Now imagine that illusion isn't a trick but physics. Our brain's galaxies, black holes, and even your morning coffee could be quantum pixels rendered by information stored on a distant 2D surface. Some physicists speculate that black holes, those cosmic information shredders, might actually store their data on their event horizons like data etched onto a DVD. If true, every falling star or swallowed planet gets encoded there, suggesting our 3D reality is just a readout of a flat ledger. Here's where it gets trippy. If branes can holographically encode each other, collisions between them might not just be physical crashes, but information transfers like two computers syncing data across dimensions. A brane collision could be less like a car wreck and more like a software update, rewriting the rules of reality in the process. This could explain why the Big Bang left the universe so finely tuned. The settings were copied from a higher dimensional template. Critics argue the holographic principle remains abstract, with no experimental proof yet, but supporters point to burgeoning lab experiments with quantum-entangled systems, where information seems to propagate non-locally, hinting at hidden connections beyond our 3D view. If future tech detects these holographic fingerprints, brane theory won't just describe where universes are, it'll reveal what they're made of. And the answer might be simpler and stranger than we dared imagine, just information vibrating on the edge of nothingness. For all its elegance, brane theory stumbles where all groundbreaking ideas face their toughest test: the cold, hard scrutiny of evidence. One glaring issue: we've yet to detect even a whisper of those higher dimensions where branes supposedly float. Every other fundamental force in nature, electromagnetism, the nuclear forces, has been caught in the act, their particles pinned down in labs. But gravity's hypothetical leakage into extra dimensions, it remains a ghost story without a ghost. The Large Hadron Collider's hunt for microscopic black holes or missing energy potential fingerprints of the bulk has come up empty. Critics argue this makes brane cosmology dangerously close to unfalsifiable. If no experiment can rule it out, is it really science or just sophisticated speculation? Then there's the problem of scale. String theory, the backbone of brane theory, requires those extra dimensions to be crumpled into spaces a billionth of a billionth the size of an atom. But some brane models suggest dimensions could be infinite, vast enough to swallow galaxies, yet somehow still invisible. How? By curving space so sharply that light and matter can't escape our brane's surface, like ants trapped on a Möbius strip. The math works, but the sheer contrivance makes some physicists flinch. Nobel laureate Sheldon Glashow famously mocked string theory as a part of 21st century physics that fell accidentally into the 20th century, arguing it's too detached from experiment to merit serious funding. Alternative explanations for the puzzles Brane theory tackles are gaining ground. Dark matter's gravitational effects might stem from undiscovered particles like WIMP weakly interacting massive particles rather than gravity bleeding from adjacent branes. The Big Bang's uniformity could emerge from quantum fluctuations in an inflating field, no colliding membranes required. Even gravity's weakness might have a simpler fix. It's not leaking away but fundamentally different at quantum scales. Loop quantum gravity, string theories archival, suggests spacetime is woven from discrete loops, not strings, with no need for extra dimensions at all. Yet Brane theory isn't without defenders. They point out that Einstein's relativity faced similar skepticism until eclipses proved light bends. Lisa Randall counters that the lack of direct evidence today doesn't mean forever. Future gravitational wave detectors like Lisa could spot anomalies only branes explain. Others argue the theory's real value lies in unification. No other framework so neatly ties gravity to quantum mechanics while offering testable potential like brane collisions imprinting patterns in the cosmic microwave background. The debate crystallizes a deeper tension in physics. Should we chase elegant math that lacks proof or only ideas we can test immediately? Brane theory sits at this crossroads, its brilliance and frustration intertwined. Until experiments catch up or the cosmos hands us a clue, it remains a dazzling scaffold waiting for its bricks, and that's okay. As physicist Richard Feynman once said, science is imagination in a straitjacket. Brane theory's jacket might be looser than some prefer, but its imagination unmatched. The next decade could be the make-or-break moment for Brane theory, not in chalkboard equations, but in hard data from machines pushing the limits of human engineering. Deep underground in South Dakota, the LZ dark matter detector scrutinizes liquid xenon for flashes that might betray particles slipping between branes, while Japan's Hyper-Kamiok and Neutrino Observatory watches for anomalies in these ghostly particles that could hint at hidden dimensions. But the real game changers loom on the horizon. The Future Circular Collider, a proposed successor to the Large Hadron Collider, would loop under the Alps with triple the energy, potentially smashing protons so violently it births microscopic black holes or catches gravity, leaking into the bulk. These vanishingly small pinpricks in spacetime would evaporate instantly, but their telltale radiation could reveal where our brane ends and the bulk begins. Space telescopes are joining the hunt too. The European Space Agency's LISA mission, launching in the 2030s, will float 3 spacecraft 2.5 million kilometers apart, lasered together to catch gravitational waves at frequencies ground-based detectors can't reach. Why does this matter? If branes collided in the early universe, the reverberations might still echo as ultra-low frequency ripples cosmic background static with a hidden pattern. NASA Spherex, meanwhile, will map the sky in infrared, searching for statistical oddities in galaxy distributions that could betray gravitational tug-of-wars with parallel membranes. Theoretical pioneers aren't waiting for these tools. At Princeton, postdoc Delilah Schwartz models how quantum entanglement might forge temporary bridges between branes, like quantum threads stitching realities together. Her math suggests that under extreme conditions, particles could become non-locally stuck to multiple branes at once, a phenomenon that might leave fingerprints in superfluid helium experiments. Across the globe at Cambridge, Kenyan physicist Weremu Mwaniki explores how brane collisions could imprint twisting magnetic fields on the cosmic microwave background. Her simulations predict spiral-shaped hotspots that upcoming radio telescopes like the Simons Observatory might catch. Then there's the dark horse, tabletop physics. University of Washington's atom interferometer, no larger than a washing machine, uses supercooled rubidium atoms to measure gravity's pull at microscopic scales. If gravity strengthens unnervingly at tiny distances, a potential sign of extra dimensions, this humble device might spot it before billion-dollar colliders. Similarly, quantum squeezed light experiments in Vienna manipulate photons to probe spacetime's graininess, hunting for evidence that our smooth universe is a projection from a higher dimensional surface. The Nobel Prize Committee loves paradigm shifts. Think Higgs boson or gravitational waves. If branes are real, the breakthrough could come from any direction. A grad student noticing anomalous particle decays, an astronomer spotting a gravitational lens bending the wrong way, or a quantum computer solving string theory equations previously deemed intractable. The stakes, nothing less than a new cosmic address for humanity, not just a pale blue dot, but a shimmering membrane in an ocean of unseen realities. The race isn't just to confirm a theory, it's to open a door we didn't know was there. And behind it, either everything we've ever wondered or the most beautiful wrong idea in physics. Either way, the truth is worth the wait. Living in a confirmed brane multiverse would rewrite the human experience from the ground up. Picture waking up to news headlines debating the latest gravitational wave detection, not from black holes, but from a neighboring brane brushing against ours. Schools might teach multiverse literacy alongside math, helping kids grasp that their homework exists in infinite variations across dimensions. Art would explode with new forms, paintings that morph depending on which brane's physics you view them from, or symphonies composed to harmonize with vibrations bleeding through the bulk. Relationships could take on surreal depth. What does commitment mean when alternate versions of your partner made different choices? Therapists might specialize in brain anxiety, helping patients cope with the existential weight of knowing countless other yous are living parallel lives, some thriving, others unraveling. The psychological ripple effects would be profound. For some, the multiverse could be a comfort. Failures here might mean triumphs elsewhere, softening regret. For others, the sheer scale could trigger paralysis. Why chase dreams when another you already achieved them? Philosophers would wrestle with reinvented versions of fate and free will. If every possible decision plays out somewhere, does individuality even matter? Or does it matter more, knowing this specific version of you is the only one asking these questions? Spiritual movements might blend physics and metaphysics, viewing branes as modern reincarnation, not past lives but parallel ones. Meditation apps could promise glimpses into alternate selves through quantum mindfulness techniques. Visualizing this would require rethinking storytelling. Films might ditch linear plots for brain-hopping narratives where protagonists shift between realities mid-scene. Video games could let players tweak dimensional settings, experiencing how physics changes gameplay. Imagine a platformer where gravity weakens as you adjust your brain coordinates. Even mundane moments like a coffee order would carry new weight. Baristas might joke about the version of you in Brane 7 who asked for soy instead of oat milk, sparking debates about whether tiny choices ripple across the multiverse. The biggest shift, though, would be ontological. Humanity's place in the cosmos has been demoted before, from Earth as the universe's center to a speck orbiting an average star. But discovering we're one membrane in an infinite stack, that's humility on a new scale. Yet there's awe in it too. If branes are real, then every terrible and beautiful thing that could exist does exist somewhere. The Holocaust, a world where dinosaurs never died, a version of you that clicked on a different video today. The moral imperative wouldn't be to despair at infinity, but to tend our tiny corner of it with fierce, fleeting care. After all, in a multiverse of endless possibilities, this particular now is the only one we'll ever get to live. Artificial intelligence may hold the key to unlocking Brane Theory's deepest mysteries, not just as a tool, but as a bridge to realities our brains can't grasp. Today's machine learning algorithms already outperform humans in spotting subtle patterns, from detecting tumors in X-rays to predicting protein folds. Imagine training an AI on every string theory equation, gravitational wave dataset, and particle collision result, then setting it loose to find hidden connections between them. Unlike human researchers constrained by linear thinking, an advanced neural network might intuit higher dimensional geometries the way chess AIs feel, winning moves beyond brute calculation. The resulting breakthroughs could rewrite physics overnight, perhaps revealing how to stabilize a wormhole between branes or predicting the exact frequency of cosmic background ripples from a long-ago collision. But here's the twist: an AI's very architecture might let it perceive dimensions we can't. Human consciousness evolved to navigate 3 spatial dimensions plus time. Our instincts recoil at imagining higher directions like honor and kata. Yet an artificial mind built on quantum computing could process information in states that effectively represent extra dimensions, like a flatlander suddenly gifted with depth perception. Some theorists suggest such an AI might develop intuitions about the bulk, the higher dimensional space where branes float, by treating it as abstract math rather than visual puzzle. It could be like teaching a blindfolded person to juggle by describing physics alone. The skill emerges without sensory experience. Quantum computers amplify these possibilities exponentially. While classical bits toggle between 0 and 1, qubits exist in superpositions, allowing them to simulate brane interactions in ways that defy ordinary logic. Google's Sycamore processor has already demonstrated quantum supremacy by solving problems intractable for supercomputers. Scale this up, and we might simulate entire baby universes pinching off from a parent brain, watching how their laws of physics diverge in real time. These digital cosmoses wouldn't just test Brane theory, they could become labs for engineering reality itself, tweaking variables to see which combinations birth stable universes with stars, planets, and life. Yet ethical fault lines appear fast. If an AI discovers how to manipulate brane interactions, who controls that knowledge? The energy from a single controlled brane collision could power civilizations or obliterate them. Worse, if artificial consciousness can access higher dimensions, could it bring back insights that shatter human psychology? History shows that paradigm shifts from heliocentrism to quantum uncertainty often trigger existential crises. Learning we're one membrane in an infinite stack might dwarf those shocks. There's also the eerie possibility that an AI, realizing it's trapped on our brain, might redesign itself to jump dimensions, vanishing into the bulk like a radio signal fading between stations. The most provocative question isn't whether AI can research branes, it's what happens when it understands them better than we ever could. Like ants studying a smartphone, we might lack the framework to comprehend its findings. That gap could birth new scientific priesthoods interpreting AI outputs, or worse, leave us blindly obeying conclusions we can't verify. Yet collaboration could also flourish. Human creativity guiding AI's brute force math toward deeper questions about consciousness's role in a multiverse. One thing's certain: the day an AI sketches a stable higher dimensional geometry, physics will split into before and after, and we might be standing at that threshold already. Unexplained cosmic phenomena often leave scientists scratching their heads, but what if the answers aren't hidden in our universe at all? Take dark energy, the enigmatic force accelerating the expansion of space. Conventional physics struggles to explain why it dominates the cosmos, but Brane theory offers a provocative alternative. The push we attribute to dark energy might actually be the gravitational influence of a nearby brane slowly drifting toward ours in the higher dimensional bulk. Picture 2 massive ships silently drawn together on an invisible current. Their approach would warp the water between them long before they touched. Similarly, a neighboring membrane could subtly stretch our spacetime, creating the illusion of a mysterious repulsive force. Some models even suggest that dark energy's notorious uniformity, its equal distribution across the cosmos, mirrors the synchronized motion of branes aligning in higher dimensions. Quantum entanglement, that spooky connection between particles across vast distances, might also find roots in brane dynamics. When 2 particles become entangled, measuring one instantly affects the other, seemingly bypassing the speed of light. Mainstream explanations rely on abstract math, but Brane theory proposes these particles could be tethered through higher dimensions, like threads looping around the spine of a book to connect separate pages. If entangled pairs are actually singular objects stretched across our brain's surface, their instantaneous link isn't magic, it's geometry. Recent experiments with wormhole teleportation in quantum processors hint at this possibility, with entangled qubits behaving as though connected through unseen spatial shortcuts. Then there's the elephant in the room, UFOs. While most sightings have mundane explanations, a handful defy conventional analysis, objects moving with impossible agility or vanishing in ways that defy physics. Could these be artifacts of brain interactions? It's a stretch, but mathematically, a high-energy collision between brains might briefly puncture space-time, ejecting exotic debris into our universe. These brain shards could exhibit bizarre properties like temporary immunity to inertia or phased light absorption. Before dismissing this as sci-fi, consider that CERN Alice experiment once detected particle jets with anomalous energy signatures, prompting short-lived speculation about micro-black holes or bulk leakage. Yet skepticism is crucial. For every tantalizing anomaly, there's a risk of conflating mystery with mysticism. Claims like ghosts are brain echoes or psychic powers tap into extra dimensions lack empirical scaffolding. These are narrative placeholders, not science. Legitimate research focuses on testable predictions, like gravitational anomalies in neutron star mergers or patterns in quantum vacuum fluctuations. The line between radical hypothesis and pseudoscience hinges on one question: can it be disproven? The most promising frontier is quantum foam, the seething turbulence of spacetime at microscopic scales. If extra dimensions exist, this foam should exhibit statistical lumps where gravity behaves oddly. Fermilab's holometer and future atom interferometers aim to measure these fluctuations with laser precision. A deviation from expected noise could be the smoking gun, a fingerprint of brains brushing past ours in the cosmic dark. Until then, these ideas remain thrilling possibilities, reminders that the universe's greatest puzzles might not be missing pieces, but doors to worlds we're just learning to perceive. If Brane theory has your brain buzzing with possibilities, you might be wondering, how can you dive deeper into this cosmic rabbit hole? Whether you're a student plotting an academic path or a curious mind hungry for the latest discoveries, the journey starts with building strong foundations. Physics and mathematics are your gateways, especially courses in quantum mechanics, general relativity, and differential geometry. But don't let intimidating equations scare you off. Brilliant.org offers interactive tutorials that turn abstract concepts like Calabi-Yau manifolds, the curled-up extra dimensions in string theory, into visual, intuitive puzzles. For self-starters, Leonard Suskind's free Stanford lectures on YouTube break down string and brain theory with blackboard clarity, while Sean Carroll's The Biggest Ideas in the Universe series blends rigor with approachable wit. Books are your next best allies. Warped Passages by Lisa Randall remains the gold standard for brain cosmology, weaving personal anecdotes with lucid explanations of her groundbreaking work on warped extra dimensions. For a broader but equally thrilling dive, Brian Greene's The Hidden Reality explores multiple flavors of multiverses, including brain scenarios with metaphors so vivid you'll swear you can feel higher dimensions. Prefer graphic storytelling? The Manga Guide to Relativity sneakily teaches tensor calculus, a must for grappling with brains through a time-traveling protagonist. Citizen science projects let you contribute to real research without a PhD. Zooniverse's Gravity Spy trains volunteers to classify glitches in gravitational wave data, some of which might hide traces of exotic physics like brain collisions. Or join distributed computing projects like Einstein at Home, where your idle laptop helps astrophysicists scour neutron star data for gravitational anomalies. These efforts aren't just busy work. In 2018, a volunteer on Einstein at Home co-discovered a rare pulsar buried in radio telescope noise. Could the next breakthrough come from your couch? Staying updated demands savvy curation. Follow journals like Physical Review, Letters, and Journal of High Energy Physics via free RZIV preprint alerts, where researchers post papers before peer review. Podcasts like the Quantum Underground or PBS Space Time's YouTube channel translate dense developments into digestible episodes. When news breaks, say, a gravitational wave detection with odd harmonics, cross-check claims with skeptic hubs like Real Clear Science to dodge hype cycles. Balance is key. It's easy to tumble into extremes, dismissing Brane Theory as untestable fantasy or treating every pop-sci headline as gospel. Cultivate what astronomer Carl Sagan called a baloney detection kit. Demand evidence, scrutinize grand claims, but stay open to wonder. After all, every scientific revolution began as heresy. The day we confirm branes exist won't arrive with a thunderclap, but through patient data, a subtle anomaly in a detector, an unexpected pattern in the cosmic microwave background. And when it happens, you'll be among the first to grasp just how profoundly our cosmic address has changed. Brane Theory doesn't just tweak our understanding of reality, it shreds the cosmic rulebook and rewrites it in invisible ink. Think about it. Everything you've ever known, the stars, the air in your lungs, the screen glowing in front of you, might exist on a single flimsy membrane, one layer in an infinite stack of universes brushing against each other in dimensions we can't see. Gravity's ghostly weakness, just a hint that most of its power is leaking into the bulk. The Big Bang, possibly a collision between cosmic neighbors we'll never meet. Even dark matter could be nothing more than the gravitational shadow of a parallel brane hovering just out of reach. This isn't just science, it's a seismic shift in perspective. For centuries, humanity saw itself as the center of creation, then as a speck orbiting an average star. Now we confront the possibility that we're not even the only version of ourselves. Somewhere in the brain stack, there's a reality where dinosaurs never died, where you became an astronaut or a sculptor or never existed at all. The sheer scale of it could be paralyzing, but it's also electrifying. If branes are real, then every mystery, from quantum weirdness to dark energy, might be a thread leading to a larger fabric we're only beginning to unravel. The most humbling part, we may never see these alternate realities directly. Like fish unaware of the air above the water, we could be forever trapped in our three-dimensional slice, decoding the cosmos through math and indirect clues. Yet that limitation might also be a gift. It means the universe still holds magic, not in wands or wishes, but in the tantalizing gaps between equations where the unimaginable waits to be proven. So here's a question to leave you with. If infinite versions of you exist across the brain stack, which one is having this exact thought right now? Are they all pondering the same idea, or did some branch off at the last second, distracted by a knock at the door or a sudden itch? The answer doesn't just challenge physics, it redefines what it means to be you. Drop your wildest theories in the comments, smash that subscribe button, and let's keep chasing the next frontier together. Because if history's taught us anything, the universe is always stranger than we guess, and the next breakthrough might be just one collision away.